So your answer is going to be pretty close to 4,000 psi, but not exactly, okay? So you have to use those densities to get the exact value that's going to be the answer. Did you guys have a good weekend? Yeah. Sunday was gorgeous. Very nice. I wanted to go running, but I didn't have time. So if you have the answer, just raise your hand and let me know. I'm very strict with the grade cutoffs. So, for example, if you have your average, which is 89.999999, to me that's less than 90, and I'm not going to round it. Okay? It's very clear in the syllabus that says it's a grade equal or greater than 90. So 89.999. It's not equal and it's not greater than 90. So that's going to be the cutoff. Although I might make an exception, and I usually add some extra points for class participation. So if I see that you're raising your hand, if you answer to questions in class, I'm going to write down here in my notes that you actually did that. And at the end of the semester, when I see that you're very close to the jump of grade, I might go to the next grade if you come to class and you participate. Okay? So if you have the answer, just please let me know, and we'll share it with everyone. Of course, don't cheat. Don't look at the solution. You have the solution online already, right? Try to do it now, and you will save a lot of time for studying later on or for making your homework at home. Yes, you have the solution? No? You have a question? What's your question?
How do we know how much water there is?
This is onshore, and we're assuming that the water is coincides with the surface. You have the solution?
For pore pressure, 1830.4 psi.
1830,
Yes.
okay.
For litho, 4051.7
4051.
psi.
If everyone agrees with that, you have the same answer. Okay, what's your name?
Daniel
Last name?
Barrera.
Okay, Mr. Barrera, let's look at the answer here. Here you have the solution. This is the gradient density. This is G. Here I'm going the long way, just multiplying by G. And you have this is a gradient of pore pressure, gradient of vertical stress. You multiply that times depth, and here I went with the matrix solution, but you can also do it with the field units, and you get that answer, which is fairly close, okay? Maybe you did some rounding, or I did some rounding over here. It's not exactly the same, but it's correct. So that's the solution for that problem. And there is another problem over here. The problem we don't have time to solve, but right now, but you can see in the notes, and it's a non-shore case. As I was telling you before, when you go offshore, now you have to consider this depth and the weight of water on top, and that's the way you're going to get your vertical stress and your pore pressure. And that's problem number 2.3. When we were doing this, we were assuming that our densities were homogeneous, were the same everywhere. But we know that that's not true. Okay, we know that the density of rocks varies with depth. As you go deeper, usually the rocks get heavier. And in order to take that into account, we need to find a general solution for this equation. We're going to have to do now a little bit of math. So let's get started with that. This will be a general solution for vertical stress. And it's very simple, and everything we have to do is to assume a cube of rock, in which we have on top of it a vertical stress, and on the bottom there is also stress applied on that face, but there is a small difference. This is a D. That D means a variation, and this is a variation of vertical stress with depth in a given depth, and that variation is going to be due to the weight of this cube. What is going to be the weight of this cube? Okay, you're going one step further, but it's just going to be the mass of the element times gravity. So, in order to solve this simple problem, we do summation of forces in direction z. In this case, I have here, let me try it. I always get confused with this. Yeah. This is x, this is going to be y, this is going to be z. We're going to learn later on that the direction of the arrows has to go in some specific way. Summation of forces in direction z is going to be what? This is going to be a stress. And if you remember, stress is the force per unit of area, right? So SV has to be multiplied by this area A. And this one is in the direction of Z, so it's going to be positive. I see that also the weight is going to go into that direction, and the one that opposes all of that is this force here, SV plus this given variation as function of depth times delta Z. Okay, so I'm missing something. What am I missing?
Area.
The area, very well. So with this element, also we're going to be able to tell what is A. Over here, the length of the cube in this direction, we're going to call it delta Y. The length of the cube in this direction is going to be delta X. And as we were saying before, the length in direction Z is going to be delta Z. So here I can write again this equation to be delta x times delta y. What is going to be the mass of this element of rock? Remember, I'm not drawing all the pores over here, but this is a rock filled with fluids. Can you tell me how we can express the mass of this rock based on what we have seen before? I could go all the way into that, but I'm not going to go into detail into that right now. It's just going to be the bulk density times the volume, where the volume is delta x, delta y, delta z, and I need to multiply that times g. Just give me 1 second. I get this to work. Okay, there's a g, and now I have SV plus DSV dz c delta x delta y, and all of these, if this is not moving, has to be equal to 0, right? And if this is going to be equal to 0, and hopefully you can see from this equation that this term over here is the same as this one times that one, and it's negative, so this one is going to cancel out, and I'm just going to be left with this part and that part. And let me write now this one as positive, so I'm going to have DSV dz delta c delta x delta y is going to be equal to density bulk times g delta x delta y delta z, and these are the same, so the variation of vertical stress with depth is going to be just the density of the rock times g. But we're going to go one step further here, and we're going to say that this density actually is a function of depth, because we did all of this equilibrium at a given point. So our equation is valid at any point. So now we have an equation that tells us what is the change of vertical stress with depth, where depth is not a constant. How would I go if I wanted to go vertical stress at a given depth? Let's say that I have a surface over here. All of this is the subsurface. The Z starts on the surface, and at the given depth, I have a function of what is the bulk density. This is the function of Z. How would you calculate now the vertical stress?
The integral.
You integrate, right? So this is a very simple differential equation. What we're going to do is we're going to move this one to this side. So this is going to be DSV from SV at Z equal to 0 to SV at Z. And this is going to be density bulk Z from 0 to Z differential Z. So that is Z. Went over there, I put the integrals, and I'm going to make one more assumption here. This is, we know it's a free surface, okay? Remember that there is nothing here, it's just atmospheric pressure. I'm not going to get into details about that right now. So I'm going to say that SV at z equal to 0 is equal to 0. And therefore, the solution is just going to be that SV integrating this one. What is the integral of 1? 1 dx? It's just x, right? So this is x. SVZ is the integral of 0 to z of the bulk density that depends on z times g times dz. And this is our equation. That's a general equation of vertical stress as a function of depth. So depth is usually very easy to measure. G, we know G. It's a constant, more or less. It varies a little bit, but not a lot. What about bulk density? How do we measure bulk density? And now we're going into real case, okay? How would you measure bulk density in the subsurface?
Neutral log.
With either neutron logs or no? Which the density log, right? You will use the density log to measure density. With the density log, you will get a continuous measurement of density as a function of measured depth. Knowing that with depth, and making this integral, you can calculate vertical stress. And actually, you're going to do that. I'm going to give you a well logging file, .las. I think you've worked with these files before, or you will in if you're taking the class Senior Design with Dr. Daigle, you will get to see these LAS files. It's not too difficult to deal with, don't worry. I'm going to give you that file, and I'm going to give you also something very important, which is a deviation survey. Wells are not perfectly vertical. They are always a little bit deviated. So you need that deviation survey to calculate actual depth from measured depth. But then that's it. That's everything you have to do. Let me not get into details right now about how to solve this equation numerically, because now you have the integral over there.